Welcome back for the last of our episodes for the week of snow. We're now in section 2.4 on distribution shapes. So, when we think distribution, what we want to think is a distribution is a function, and like very many functions, it's easier to visualize, to discuss a function if we visualize it. So here, for example, is a distribution of heights. Because the center seems to be at about 5'4.5" inches, I think this is probably a distribution of heights of women in the U.S. And we see here both a frequency distribution, which I observe is more or less symmetric, high in the middle, low on both ends, which suggests that it might be a normal curve, or it's bell-shaped, but not all bell-shaped curves are normal curves. Okay, and then we have this black line, which is an effort at making a smooth curve that connects the high points of the frequency distribution. Okay, now let's go back and look at the definition that we had. So, table, graph, or formula that tells us both what the observations in our collection are and how often they occur. So, in some cases, we can write the function as an equation, the way that we would do in algebra. In other cases, it's more convenient to show a frequency distribution, particularly in statistics, the frequency distribution rules. Here are other common distribution shapes. There are many bell-shaped curves, and as I said before, not all of these are normal curves. Those two are not synonyms. We will have other bell-shaped distributions which are very important. I want to mention some of the others here. Uniform. A uniform distribution is what you would expect to get if you throw what's called a fair die, singular dice. So you take a six-sided die, or let's say six, and you throw it again and again and again and again. You would expect to get the same number of ones that you get of twos, that you get of threes, fours, fives, and sixes. That's a uniform distribution. We have two skewed distributions here, right skewed and left skewed. My mnemonic for which one is which is that skew sounds like Q or tail. Right skewed has this long, skinny tail. What's an example of a skewed distribution? For example, sports salaries for men in professional sports. We have all the guys on the sidelines, and then we have a few stars who are making really big money out here. There are not so many of them, so they're out here. And then in this big bump, you have all the fellows who are the journeyman players, who are getting more modest salaries. Another distribution that I have referred to in class is this bimodal. Mode is the number that occurs most often. In this case, we have apparently two numbers that occur most often, two observations. One at one end, one at the other, and while you would think that someone like me collecting statistics on student performance might have more bell-shaped curve with people mostly average and then some really good and some really not so good. What I'm more likely to have in most cases is a lot of people at one end, a lot of people at the other end, and then in the middle, not as many as I would have expected anyway. Another look at the definition here. Okay, all the values of the observations and how often they occur. So, very often simply illustrated with the frequency distribution. Okay, here is a pair of graphs in which we see the number of people in households. We have no zeros. There would be no household if it had no people in it. Somewhere between 20 and 25% of households with just one person living by himself or herself. Lots with two, either a couple or a parent with a child maybe. And then households with more people. There's really no upward limit on this. I suppose there are practical limits. Then in the picture on the right, we have a curve overlaid on the bumpy frequency distribution. This one is plainly right skewed. Not very many observations at the high end on the x-axis. Our next thing to discuss is the similarities and differences in population and sample distributions. So here's the same population frequency distribution for household size. So I don't know what this population might be, but let's suppose that it's all the households in one city, something small enough conceivably to take a census and find values for every household in the population. Then we have samples from the population. We don't know how big these sample sizes are, but we observe that they all seem to have approximately the same picture as the population distribution. Not identical. We wouldn't expect a random sample of the population to be identical to the population itself. But on the other hand, a proper random sample should give more or less the same shape, the same distribution that we find in the population. This is a very important observation because, as a rule, it is not practical to take a census of an entire population. We have to do sampling. So what do we do with the variability between the samples and the population itself? Well, that's a big part of our study. In the first place, we want to have proper random samples. In the second, this variability we are going to account for by making adjustments to the distribution that we get. And in the third place, this is where our measure of confidence in the sample comes in. We don't say this is the same. We say we're 95% or so confident that the values that we get out of the sample, such as a mean or the distribution itself, are within a margin of error of the same values for the population. Let's look back at the slide before and see what we have. So we have a population distribution of a variable such as household size, and then a sample distribution. And let's look at the next slide. This is very important, that statistics is a science built around the fact that a random sample approximates the population. And the second part of this is the larger our sample size, the better the approximation is going to be, as a rule. So what we're going to do, a part of our study, is just how big is that appropriate sample size so that it does give us a good reflection of the population. And that's the end of my discussion of section 2.4. I would like for you to look at all of the problems at the end of the section and look at the solutions in the back of the book too. And if what you think is the answer is not the same as the answer given in the back of the book and you have a question about that, please bring it to class. And then problem number 108, do that either by hand or using StatCrunch and answer the questions that are included there. And last of all, get some fun out of this snow. I'm certainly going to try to. Thank you for listening, and I expect to see you on Friday the 29th.